In Lesson 1.2, Evaluating Limits Graphically and Numerically, we will begin our exploration into limits. We'll work with a working definition of limits, and we'll see exactly what they are, both in a table, that's numerically, and on a graph, of course, that's graphically. Through looking at limits numerically and graphically, we'll get a feel for what they are, how they arise, and further in this chapter, we'll see how they're used as we move along in our study of calculus. Before we begin working on any of our notes, I first want to discuss what a limit actually is. And it's very simple. When you hear the word limit, I want you to think approaching. In other words, the limit of a function as x approaches some value is what y value that function approaches. Now, sometimes we can direct substitute. It really matters if it is a continuous function or not. Let me give you this as an example. If we look at the limit as x approaches 1 of the function x squared plus 2, this is just a function I'm making up here, x squared plus 2 rather, is a continuous function. There are no holes, no discontinuities, no breaks, nothing like that. And because of that, this ends up being a very easy limit to evaluate. I can simply stick that x in there, direct substitution, and get that the limit of this function as x approaches 1 is simply 3. That's the y value. If I wanted to, I could make a chart of values, or a t-table, or however you want to call it, of x and f of x. And let me just start at -1 and move up from there. And if I do that, what am I going to get for f of x? Well, when x is -1, I'll get 3. When x is 0, I'll get 2. When x is 1, I'm back to 3, and so on and so on. This would be 6, and then of course when x is 3, I would get 11. So, simple enough. In a continuous function, all I need to do is really just direct substitute. But what happens when I don't have a continuous function? What if there are holes or breaks or discontinuities of some sort? In a case like that, there's two ways I can approach this. I can make a table like what I've done here and just get really close into that value. That should give me a good idea. Otherwise, what I can do is I can draw a graph of it somehow, take a look at the graph, and see where I'm approaching. Again, if it's a continuous function, I can direct substitute, no problem. However, in a discontinuous function, I really do need to look at some advanced methods of doing that, and we will look at those in this lesson. That being said, why don't we go ahead and take a look at our first example, which will involve doing a table of values. In our first example, we have what I consider to be a pretty nasty function to work with here. It does have a square root in the numerator and all this crappy stuff going on. But regardless of that, we have a table. We want to find the limit of the function. In other words, we want to find the y value that this function approaches as x gets closer and closer to -3. Now, we could go ahead and try a direct substitution, but hopefully you can see what would happen there. If we plug in -3, what we're going to end up with, if we simply say f of -3, let's say, we get something pretty nasty. In fact, if I calculate correctly, we'll get 0 over 0, and that, of course, is an indeterminate fraction, so that's not going to work. However, I will tell you, this function does have a limit. There is a y value that this function approaches as x gets closer and closer to -3. And so what I've done is I've laid out a table for you here, and we're just going to go through and fill out y values in this table. And once we get here, of course, what we're going to get is a does not exist. And so the function doesn't exist at -3, but that does not mean that there's no limit. Well, if we go ahead and fill out these values, and this is something I've done beforehand, so I can just go ahead and fill these in, what we would get here would be -0.2501. Doesn't seem too special. Here, however, we would get -0.25001. Very interesting. It seems like it's getting closer to something. And if we fill this in, I might not have room in the box there, so I'll just write it down here. We'll get -2.25001. And so it does seem like we're getting really close to -0.25. Well, from the left, that might work. This is actually approaching negative 3 from here. Let's approach negative 3 from this direction and see what happens. In fact, if we start right here, what we'll get is negative 0.2498. Now, some of you might stop there and say, well, that's really close to negative 0.25. That must be our answer and we're done. But I caution you, actually fill out the table, see what happens. There's a lot to be learned here, and you really should not jump to conclusions. However, if I keep filling in boxes, this is negative 0.24998. And so you see we are getting closer. And this last box right here, negative 0.24999. And then there's probably an 8 in there somewhere further down the line. So, if we look at this, as we come in from the edges, what number are we getting really, really, really close to? We already said the function doesn't exist, but we do, in fact, get really close to negative 0.25. We'll learn much later in the year how to actually work this out. But here you can see in a table that negative 0.25 is what the y value approaches as x gets closer and closer to negative 3. Now, I do caution you here again, if you use big numbers in your table, for example, negative 1, negative 2, negative 3, you might fail to see the pattern. You really need to get closer and closer and closer by very small increments. You can see here we're talking about 1/100ths, 1/1000ths, 1/10,000ths. So really, really, really narrowing in on that negative 3. Well, that being said, why don't we take a look at another very similar example and see what happens in that one. So, in example B, we have a very similar example that we're going to try to do. We have the function sine of x over x, and we're going to try to find the limit of that as x approaches 0. Real quick, do this in your head. What do you get? Plug in 0. Well, again, you get 0 over 0, and that, of course, is a problem. So, if we actually go ahead and work out these numbers again, again, I've done them before, but I challenge you to go ahead and do it. Don't just copy down my numbers. See what you get, and just to make sure that we do get the same things. Nevertheless, I'm going to go ahead and write down what my calculator told me, which is when x is negative 1/10th, I get 0.998. When x is negative 1/100th, I get 0.99998. And when x is negative 1/1000th, I get a whole bunch of 9s. Wow. Let's see here. I don't feel like counting those, but it's a whole lot of 9s. 9, 9, 9, 9, 9. A bunch of 9s, and then an 8. All right. So based on that, from the left anyway, from the negative values approaching x, it looks like I'm getting closer and closer to 1. What happens when I start above 0 and come down? Interestingly enough, I get the same values. There's 0.998, 0.99998, and then this ridiculous mess of 9s with an 8 at the end. Not quite sure how many 9s, but there we go. So again, when I plugged in 0 to the function, I got nonsense. But you can look here and see that sure enough, although there is no value for f of 0, the limit as x approaches 0 is in fact equal to 1. Well, just for fun, and because we are about to segue into looking at these graphically, pick up your graphing calculator. Put this function into your y1 and graph it. If you do that, you should see a graph that maybe looks something like this. Let's see here. I'm looking at my graphing calculator, and it looks something more or less like that once I set the window correctly. Now, of course, what I'm interested in is what happens when x approaches 0. So let's see here. Here's x is negative, and it's working, and I'm approaching 0 from the negative side. And over here, starting at point 1, well, not starting at point 1, but starting at the positives, as x approaches 0, I seem to be approaching here on the y. Now, we did say that it's undefined when x is 0, but maybe you can see that the limit itself, they're both approaching the same. From the left, from the right, they're both approaching the same thing. And in fact, that is the value 1. So, very interesting. Limits are simply what y value we approach when the x value approaches a certain number. And with that being said, and now that we've actually looked at a graph, why don't we look at a bunch more graphs, some continuous, some discontinuous, and maybe you'll notice some patterns in these. For the next 6 examples, we're going to take a look at limits graphically. That is, I want you to get out your graphing calculator, actually graph these functions, and see if we can't use that picture to try to determine the limits of these functions as x approaches some given value. Again, remember that when we say the limit, we're talking about approaching, and what we're looking for is the y value. So let's go ahead and begin with this one here. The limit is x approaches 1 of the function x squared plus 2. Sound familiar? It should. In fact, here is a graph of that function, and let's go ahead and talk about that graph real quick. Notice that I've put a barrier where x equals 1. The reason I did that is we are not worried about what the value of the function is when x equals 1. We're only looking at what y value are we approaching. So as we come from the left, and imagine a moving point on this graph, it would come down and then start coming back up as we approached 1. And what value would we be coming close to? It kind of looks like 3. At least it looks like that to me. As we come from the right, we'll be coming down in this direction. And again, it seems that we're approaching some value about right here. And in fact, we are. This is a continuous function. We could have used direct substitution, but the value of the graph is very important. We're not interested in what happens at x equals 1, simply what happens around x equals 1. And it looks like we're getting really, really close to y equaling 3. And so the limit of this, as x approaches 1, is in fact 3. Let's take a look at another example that's very similar, very, very similar, and see why, in fact, the graph could fail you if you're not careful. In our next example, we have almost the same function, except this time it is piecewise, and when x equals 1, this function is going to be defined as 1. How does that look graphically? It looks almost the same. In fact, I'm going to use almost the same graph that I did before, but we're going to notice a little bit of a difference here. This time, our graph is going to say when x equals 1, that the y value is 1. In other words, there's going to be a discontinuity right here, a hole, if you will, and the function will be defined at that point down there. Now, is this a continuous function? You should be able to answer that question very easily. No, it's not continuous. And so direct substitution actually won't work. If you do direct substitute, what will you get? Well, if you plug x is 1 into this piecewise function, looks like we'll get 1. And that's according to this second line of the piecewise function right there. However, remember what I said before. We want to look at what y value we're approaching, not necessarily what y value we get. And so, if I follow this function from the left, just like in the last example, it'll drop me off over there. And if I follow it from the right, this function will drop me off about right there. And so this point down here is essentially irrelevant. In algebra, I would say f of x equals 1, certainly. But here, dealing with limits, the limit of this function as x approaches 1 is still going to be not here, but right here. Yes, it's true. The function is not present at that place. Nevertheless, that is the limit. Don't look at that location. Look around that location, and you'll see that that is the limit. Of course, you might have thought that this might be one that does not exist, but we'll get to a couple of those here shortly. Well, with that, let's take a look at another example that starts to get a little bit hairy. In example E, once again, you can try a direct substitution type method and see how it works out for you. Clearly, if you stick 5 into our given function, you're going to get 1 over 0. In fact, you might recognize this almost as a transformation of the function 1 over x squared, simply move 5 units to the right. And really that's what it is. But if we go ahead and take a look at this function, I put a dark blue line here at x equals 5. Not because I believe that's an asymptote, even though it might be, but because that's where I'm trying to find the limit of this function. And so I'm not interested in what happens at x equals 5, but rather what happens around x equals 5. Now, as I approach x equals 5 from the left, notice what happens to this function. It seems to be going up, 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 up forever. And as I approach from the right, it seems to be going up, 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 up forever. Is it ever going to cross x equals 5? You've learned about asymptotes in previous courses, so you know it will never hit x equals 5. And in fact, there is no value that this function approaches from the left or the right. A lot of times, and this is a murky point, we can say that this function does tend towards infinity. After all, from the left, we're going up to infinity. From the right, we're going up to infinity. Unfortunately, infinity is not really a number or a value, so we can't say that the limit equals infinity. What we can say here is, in fact, that the limit does not exist. However, later on you'll see that it is important to note what is actually going on. And we could say that the function tends to infinity. That would tell the well-versed mathematician that both from the left and the right, the function is increasing forever. As we say, it is increasing without bound. And so right here is our first example of when a function, when its limit might not exist. We'll explore a couple more in the coming examples. In example F, we have yet another piecewise function. Nothing to scare you, of course. It's a very simple function, two linear functions separated by a constant of really just 1. However, this piecewise function does break at x equals -4, which is exactly where we're trying to evaluate the limit. So if you do a direct substitution where x is -4, of course, that's going to lead us to the second part of the definition of this function right there. And what we would end up with actually is -6 right here. That's the old algebra way of doing it. That's the direct substitution. That's not what we're looking for here. Rather, let's go ahead and see what happens as we approach -4 from the way negative values. And you can see as this arrow goes that we're going to end up at about -7 or so. Meanwhile, if we do the same thing, we approach x equals -4 from the positive side. Now we're going down this function, and it looks like we're going to end up with -6. Now, -6 is what we got in the direct substitution, but what's happening around here? What's happening on the blue line? Or rather, not on the blue line, but around the blue line, it completely breaks apart. We're not getting to the same thing from the left as we are from the right. There is a discontinuity. There's all kinds of issues with this. And because of that, what we have to say is that this limit, the limit as x approaches -4 of this function, we have to say that it does not exist. In order for it to exist, the limit has to be the same from the left as it is from the right. They have to be approaching the same value. Here, they are not. And now we've seen the second way that a limit can fail to exist. Before beginning example G, I want you to notice the similarity between the function present in this example and the function that we saw when we were looking at example B earlier this lesson. Surely you'll notice that the real difference between these two is that in example G, the sine function has an extra 2 in there, affecting the period of it and all that good stuff. The frequency, as some people would call it. So, if we go ahead and take a look at this one here, and let me go ahead and bring up the graph of it, it looks just like the graph that we saw when I kind of introduced you to graphing back on example B. This time, if we go ahead and follow this, we'll follow from the left, and notice what happens. Just like in example B, we're approaching a value, and if we go from the right, notice again, we're approaching a value. This time, fortunately, we are approaching the same value from the left and right, and that is going to be the value of our limit. In this particular case, that limit is equal to 2. Now, this is very interesting. In example B, just to refresh you, we looked at the limit as x approaches 0 of sine of x over x, and we determined that to be 1. Here in example G, we did a very similar function, except we put a frequency of 2 into the function. Notice what happened. Just for fun, I want you to try doing the limit as x approaches 0 of various values of the frequency. I'm going to call them sine of kx over x. And see what you get when you try different values for k. What I want you to be able to do is to fill in the missing part of this. The limit as x approaches 0 of sine of kx over x. The limit of that would be equal to, again, I'm not going to give you the answer here, but pick up your graphing calculator, plug in a few different values of k, see what happens. Very interesting, and that could come up again later on in the year. In fact, multiple times. Don't forget it. Now that we've gotten through most of the examples in this lesson, you've been able to determine 2 reasons why a limit might not exist. What I want to do here is formalize that before we get to our last example. Little hint for you, the last example will be the 3rd reason, but let me explain it before we get there. If you recall, the first reason why a limit might not exist is simply if the limit from the left, in other words, the limit coming from the negative values or the more negative values, if that does not equal the limit from the right, then we definitely don't have a limit to the function. As we approach from the left, as we approach from the right, if they miss each other completely, then there's no limit. The flip side of that is if they do seem to approach the same thing, then we're good to go, no problems. Alright, well, the second reason we could have that a limit might not exist is if the limit from the left or the limit from the right, so I'm just going to say the limit from the left or right, if they go to infinity or negative infinity. If this happens, we can say that the limit is tending towards infinity or tending towards negative infinity. But in order for there to actually be a limit, there actually has to be a value. And infinity, negative infinity are not considered real values. That you learned a long time ago. So what is the third reason that a limit might not exist? This is a strange one, but if you have a function that's coming very nicely, and then all of a sudden it just kind of starts going like this, just starts kind of going all crazy, we won't be able to find the limit in all that mess. And what we're going to do is we're going to call that an oscillating function. If the function oscillates around the value that we're looking for, then there is no limit. How exactly would that look? Maybe I didn't give a very good description of it with my hands, but maybe if we have something that goes like this, and then just starts to go crazy, it could even out later on. But in that crazy portion, we're not going to be able to find any limits. You want to see an example of it? Excellent, because that will be our last example of this lesson. So for our last example in this lesson, we're going to take a look at what I'm already going to tell you is an oscillating function. Oscillating functions most often happen inside of trigonometric functions. In this particular example, it happens inside of a sine. Could be inside of a cosine or any of the other ones. While I say that's the most common, those are not the only ways it could happen. So always be on the lookout for a function that just starts to go crazy or kind of haywire in the middle of anything. I've gone ahead and graphed this for you already, although I certainly invite you to graph it on your calculator so that you can zoom in, zoom out, and see if what I'm saying is a load of hokey, or if I'm telling you the truth. Just looking at this picture here, you see how it's pretty smooth, then it starts to go haywire, and then it gets smooth again. Unfortunately, we're trying to find the limit in the middle of all that mess, and what we have to say is that the limit does not exist. However, maybe if we were to zoom in on this function a little bit, it would be easier to see. Let me zoom in so that our window is from 0 to 2, and you can see that, indeed, it's going haywire in there. It's going crazy. I'm not going to zoom in anymore, although if you have it graphed in your calculator, zoom in as much as you like. You'll find it never evens out, it never approaches any values, it just oscillates. It goes up and down very, very fast. And so, that's going to conclude our basic study of limits, at least looking at them numerically and graphically. There are other ways of doing limits that we'll explore in the coming sections. But just remember the three ways that a limit cannot exist. Remember that numerically you can find the limit using a table, and always be sure to check a graph if you have that at your disposal. Remember that as you proceed with your homework, and good luck.